Hi, students. This video is my lecture on chapter 31 on nuclear physics. Okay, so we've talked about quantum physics, and we talked about application of quantum physics to the atom. All right, and so now, as we've discussed earlier, or in chapter 30, the atom, almost pretty much the entire mass of the atom is located at the central nucleus, which is about 100,000 times smaller than the atom. And this is work this was a discovery that was made by Rutherford. We talked about that in chapter 30. So in chapter 30, we discussed that almost all the mass of the nucleus of the atom is located in a central dense nucleus, which is on the order of 10 to the negative 15 meters across. Whereas the atom is on the order of about 0.1 nanometers across. All right, usually about an angstrom. Angstrom is 10 to the negative 10 meters, all right, or a tenth of a nanometer. All right, so that's what we're talking about. We're talking about that the nucleus is extremely dense. I mean, this discovery was first made by Lord Ernest Rutherford and his team. Okay, and so again, this is just a rehash of what we learned in chapter 30 that's now leading us into chapter 31. So chapter 31 is all about the nucleus. We're now going to focus on the nucleus. So of course, you know, quantum physics is the physics of the submicroscopic. Certainly, the submicroscopic includes atoms. While it includes atoms, it certainly includes the nucleus. The nucleus is on the order of 100,000 times smaller in volume than the atom. All right, and so we talk about, you know, the need to, or at least clues that a nucleus exists. And of course, you know, we discussed the gold, the shooting alpha particles from a gold foil, that experiment done by Rutherford and with his graduate students Geiger and Marsden. But before even that, in the late 1800s, we had a discovery of nuclear radioactivity. All right, and so essentially, in 1896, and I've talked about this before, 1896, that was a keystone year. French physicist, again, Antoine-Henri Becquerel, Antoine Henri Becquerel. He lived from 1852 to 1908. He accidentally found that a uranium-rich mineral called pitchblende emits invisible penetrating rays that can darken a photographic plate enclosed in an opaque envelope. All right, so there's a radioactive element, a radioactive substance called pitchblende, and it just seems like it emanates these rays all the time. Where does this energy come from? So he accidentally found, and sometimes great discoveries are found by accident. He accidentally found, it's probably good he did that because otherwise he'd be radiating himself, that a uranium-rich mineral called pitchblende emits invisible penetrating rays. That can darken a photographic plate that's enclosed inside of an opaque envelope. Okay, so accidental discovery. The rays carry energy, but amazingly, the pitchblende emits them continuously without any energy input. All right, this is one of the things that we couldn't understand earlier. So the rays carry energy. And amazingly, they do so continually. Without any energy input. Right? So this is apparently a violation of the conservation of energy. I mean, where's this energy coming from? Initially, I mean, again, this is 1896. We have not yet had relativity. Einstein had not, was barely like 17 years old at the time, right? So there wasn't any Einstein yet, and quantum physics had not started. And so again, this was, something that we're talking about in 1896. Nobody really had any idea what was causing this to happen. So again, 1896, Antoine Henri Becquerel, French physicist, accidentally found that a uranium-rich mineral called pitchblende emits invisible penetrating rays that darken a photographic plate that's enclosed in an opaque envelope. The rays carry energy. Amazingly, they do so continually without any energy input. Where is this energy coming from? Where are these rays coming from? All right, and so again, that's a mystery. So you don't get something for nothing, right? And so apparently, I mean, at first blush, it looks like there's a violation of the conservation of energy. So this activity or this phenomenon appear to be a violation of the conservation of energy. Okay, and but we actually understand that it's caused by a conversion of a small amount of mass into energy. So we now understand that this energy comes from the conversion of a small amount of mass delta M into energy by Einstein's famous formula E equals delta M times C squared. That is what Becquerel was noticing. But again, Albert Einstein didn't do this work for another 9 years. So nobody had any idea about E equals delta MC squared. Nobody had any idea about relativity. And this discovery was 9 years before Einstein's epochal year. All right, now, so we have an entirely new field we're talking about here in this chapter. So again, this is what Becquerel is discovering. These rays they're nuclear in origin. All right, and so again, they're highly energetic, and I'll kind of talk about what arguments you can use to understand that the rays are nuclear in origin. All right, so again, it became evident. So it soon became evident to Becquerel that the rays originated from the nuclei of atoms and have other unique characteristics. And we'll explain that in a moment. So the emission of these rays, let's come up with some new definitions, right? We're talking about a new study here, and so we have to kind of define some terms here. All right, so the emission of these rays is called nuclear radioactivity. Nuclear radioactivity. All right, new term, nuclear radioactivity, or simply radioactivity. Sometimes we just talk about radioactivity. So this behavior is called either nuclear radioactivity, basically determining a source, or for short is oftentimes just called radioactivity. The rays themselves are called nuclear radiation. nuclear radiation. All right. So again, Becquerel became evident that the rays originate from the nuclei of atoms, and I'll give the arguments for this in this lecture. The emission of these rays is called nuclear radioactivity, or just simply radioactivity. The rays themselves are called nuclear radiation. Okay. What else? The nucleus. All right. So let's nuclear radioactivity or nuclear radiation. All right. Let's continue on. We have some more terms to define. All right. The nucleus that spontaneously decays destroys part of its mass. To emit radiation is said to decay. Remember, this energy is coming from at the expense of mass. It's a mass to energy conversion. So the nucleus is actually losing mass. Mass is being turned into energy. Okay, so a nucleus that does this is said to decay. So a nucleus that spontaneously destroys part of its mass to emit radiation is said to decay. All right. Now, a substance that or object that emits nuclear radiation is said to be radioactive. A substance or object that emits radiation is said to be radioactive. All right. Again, a lot of new terms here in this study. We're talking about nuclear radiation. All right. Nucleus that spontaneously destroys part of its mass to emit radiation is said to decay. A substance or object that emits radiation is said to be radioactive. So a pitch blende is radioactive. Now, why do we think that? I mean, what evidence suggests that these rays, from Becquerel, the Becquerel discovered? What evidence suggests that it is from deep within the nucleus? Why do we think that? All right. So the next question we want to ask. Okay, here's our terms. All right. Now, what evidence suggests that these rays come from the nucleus? All right. What evidence suggests that these rays come from nuclei? All right. Well, first, the radiation is found to be associated with certain elements, such as uranium. All right. So, first of all, not every element is going to emit radiation. Only certain elements. All right. So, first of all, the radiation is found to be associated with certain elements, such as uranium. So some certain elements always, I mean, more often than not, come up to be radioactive. Other ones are not. So again, radiation is found to be associated with certain elements. Number one, radiation does not vary with chemical state. That is, uranium is radioactive whether it's in the form of an element or a compound. So however uranium appears, it doesn't really matter. It's still radioactive. So radiation does not vary with chemical state. All right. So that is uranium is radioactive whether it's in the form of an element or a compound. Okay. So again, irrespective of how uranium comes in an ore, it comes as just pure uranium, or it comes as part of a compound, it is still going to be radioactive, irrespective of its chemical state. All right. Now that's not the case for, I mean, if this behavior is depending upon, for instance, valence electrons in an atom, well, its chemical state makes a big difference regarding its properties. And you take, you take hydrogen and oxygen. Both of those elements are highly flammable. You put them together, you make water, right? So the fact that you put elements together in a compound, they will have vastly different behaviors than if the elements were pure by themselves, right? That's what you see in chemistry. Chemistry is the science of valence electrons. Well, you see that uranium has this behavior irrespective of however it forms. So whatever is going on, it's not in the valence electrons. It's not atomic. Otherwise, uranium would react differently whether it's in a compound or an element. All right. So radiation does not vary with temperature, pressure, or ionization state of the uranium atom. So again, all these other things that would be important in chemistry does not matter for this particular type of radiation. So radiation does not vary. Temperature, pressure, or ionization state of the uranium atom. All right. So again, all of these factors affect chemistry. All these factors would affect atomic physics. You vary the temperature, what happens? Well, an object may melt, for instance, or it may evaporate, or whatever. And that's going to change the properties of the substance. If you're talking about chemistry, solid water, we call ice, is very much different in its properties than liquid water or vapor. However, it doesn't affect radiation. Uranium is going to be the same. It's not affected by temperature, pressure, ionization state, none of this. Radiation is still going to occur. None of this is affected, right? So all of the above would affect electronic transitions in an atom. So radiation cannot be atomic. And when I say atomic in nature, I'm talking about the energy levels that we talked about back in chapter 30. And there's one other piece of evidence, all right? So again, all of this is evidence, so again, radiation is found to be associated with certain elements, uranium. So anytime you have uranium or plutonium or radium or some of these other ones, you're gonna see that they're being radioactive. Does not vary with chemical state. So it doesn't matter if the let's say for instance uranium is part of an ore or an element or a compound. It doesn't matter. It's still going to be radioactive. It's still going to be it's still going to be emitting rays as it would otherwise. Radiation also does not vary with temperature, pressure, or ionization state. Again, all of these factors would affect something that's atomic. All right. Now, there's another piece of information that suggests that it's nuclear, and that is how large the energy is of the emitted rays. Okay, these emitted rays again are in MeVs, as we talked about earlier. All right. So again, more evidence. Let's go and continue. And this is all evidence that kind of compares with chemistry or with atomic physics, saying there's no way that this could be atomic. Now, on the other hand, we know a little bit about the nucleus now. So the huge energy emitted during each event cannot be atomic. So again, the energy emitted in each event is an MeV. i.e. 10 to the 6 eV, a million electron volts. That's the kind of energy we're dealing with, all right, per event. Atomic transitions have energies in eV, a few eV, few electron volts. Right, and so again, there's no way that, and again, this comes about, as we'll see, because of how squished together the nucleus is. It is shoved together by incredible forces. So if anything comes out of that, it's going to be flying out of there with a very large amount of energy. Again, it has to be nuclear in that respect. There's nothing in the atom. There's nothing like in the electronic transitions of an atom, of its energy levels, that are going to be able to produce something in the 10 to the 6 EVs. The greatest you're going to get are X-rays. You have the low level vacancies that get filled up in X-rays. We saw that was in KeVs, kiloelectron volts. This is a factor of 1,000 greater than that. Again, this is a factor of 1,000 in energy greater than X-rays. Very large X-rays. X-rays are as large in energy you're going to get from electronic transitions. You're not going to get any greater than X-rays. For you to get, so there's nothing in an atom, nothing in the electronic transitions of the energy levels of an atom that are going to give you energies in the million electron volt range. It's not possible. All right, again, another piece of information that says it has to be from the nucleus. Again, we'll get to these arguments more and more, but again, this is these are the arguments we're trying to figure out. Okay, I have these strange behavior of these rays from pitch blende. Where do they come from? And so So again, the studies done by Becquerel showed that they come from the nucleus. All right. Now, Becquerel worked with another great physicist, a couple of them, Marie and Pierre Curie. Worked with Becquerel. All right. So again, we go to 1898 now. Marie Curie Now, Marie Curie lived from 1867 to 1934. Okay. Then a graduate student. Working on her PhD. Married the already well-known French physicist Pierre Curie. Pierre Curie lived from 1859 to 1906. Okay, so she married him in 1859, and she began her doctoral study. And Marie Curie began her doctoral study on Becquerel's rays. All right, so we have two other great physicists now involved with Becquerel. Those are the Curies, Marie Curie and Pierre Curie. All right, so she started, started studying or working on her PhD. Now, in her process, Marie and Pierre Curie soon discovered two new radioactive elements. So one, she was named polonium after Marie Curie was actually originally from Poland. So polonium was after her native land, and then radium because it radiates. So two new elements that are added to the periodic table. All right. So again, the Curies work together on this. So Pierre and Marie Curie soon discovered. These are radioactive elements that were not known about yet, and adding to the periodic table. So she soon discovered two new radioactive elements. All right, polonium, named after her homeland, Poland. And radium. Basically named because it very, very radiates, glows. It radiates so much. So this element, you just look at it, it glows at you. All right. So again, that's how radioactive it is. All right. So again, Pierre, and so in 1898, Marie Curie married. So again, she was born from 1867, 1934. A graduate student, married the already well-known French physicist Pierre Curie. Pierre Curie lived from 1859 to 1906. Marie Curie began her doctoral study on these very Becquerel rays. Pierre and Marie Curie soon discovered two new radioactive elements: polonium, named after her homeland Poland, and radium because it radiates. All right. So these are elements that filled two unknown holes in the periodic table, as I said. So over a period of 4 years, Marie Curie, if you could say anything about Marie Curie, I mean, she's brilliant. She worked like crazy. I mean, she had a work ethic that you would not believe. And so she worked tirelessly in very poor conditions. Both she and Pierre, and they processed over a ton of uranium ore to isolate just a gram of uranium salt. Okay, so again, they worked very, very hard so they processed literally a ton of uranium ore to get just 1 gram of uranium salt. It took them 4 years. All right, finding uranium. So Marie Curie was, very much a type A personality. Worked very, very hard. All right, and so, again, so over a period of 4 years, over a period of 4 years, working under very poor conditions, spending their own funds. The Curies processed more than a ton of uranium ore. To get 1 gram of uranium salt. Okay, so again, this very, very, very hard work. And radium, on the other hand, was very highly sought after because it was about 2 million times as radioactive as uranium. So, finding radium is very sought after. So radium itself, this new element, was highly sought after. Because it was about 2 million times more as radioactive as uranium. I mean, it was so radioactive that it basically glowed. So imagine what it does to your health. All right, so over a period of 4 years, working under really bad conditions, spending their own money, the Curies processed more than a ton of uranium ore just to get 1 gram of uranium salt. Radium, again, one of the elements that she discovered was highly sought after because it was found that it was about 2 million times more radioactive than uranium. All right, in fact, radium salt glowed visibly from the radiation that took a toll on the unaware researchers. So again, the Curies, Becquerel, others had no idea that these rays were wreaking havoc on their body. All right, and I believe Marie Curie actually ended up dying of leukemia and had lesions on her body from all of the research that she was doing. She was handling these ores, these radioactive elements with her bare hands. So they did not know. So you're talking about something that's so radioactive that it glows. You probably don't want to touch that, but they did not know that. I mean, that's the unfortunate thing about, you talk about, well, how do you know that this is fairly poisonous, or how, well, somebody had to figure it out the hard way. And then essentially you now learn from that person. So somebody had to go figure out the hard way that something was bad for you, right? And so this is these physicists are the ones that kind of felt, that understood for the first time that, yeah, this is not good for you. This is poisonous. This causes cancer, right? But they did not know that. So anyway, so radium salt glowed visibly from the radiation that took its toll on them. All right, so this is very unhealthy to be doing this, but again, nobody knew this. So again, literally radium glowed. So going back to Curie, she was a graduate student. She completed her PhD, and both the Curies and Becquerel won the 1903 Nobel Prize in Physics for their work on radioactivity. So the three of them got the 1903 Nobel Prize in Physics for this work. So, so Marie Curie completed her PhD. And in 1903, Pierre Curie, and Antoine-Henri Becquerel won the Nobel Prize in Physics. For their work in radioactivity. All right, so Marie Curie, Pierre Curie, and Becquerel were now all Nobel laureates. Unfortunately, only 3 years later, in 1906, Pierre Curie was killed in an accident with a horse cart. So he was hit by a horse cart in 1906 and killed. So Marie Curie never remarried. She spent the rest of her life, working on physics. So her husband died in 1906. So Pierre Curie was accidentally killed by a horse cart. In 1906. All right, so unfortunate. Now, Marie Curie continued her studies for another 30 years. All right, and so she actually won the Nobel Prize again in 1911 in chemistry for the discovery of those two new elements. All right, and so she actually is one of a couple of people to win the Nobel Prize twice, and she's the only person up to this day to win it in two different fields. All right, so 1911, Marie Curie won the Nobel Prize in chemistry. For her discovery of the two new elements, polonium and radium. All right, and so she has, I mean, it's amazing to win the Nobel Prize even once. She won it twice, and she remains the only person to win Nobel Prize in physics and chemistry. All right, so Marie Curie remains the only person to win Nobel Prizes in both physics and chemistry. Nobody else has ever done that. John Bardeen won it twice in physics. So there are a couple people that have won the Nobel Prize twice. John Bardeen won it for the transistor, and he later won it for what's called the BCS theory for superconductivity. The B in BCS theory, I mean, the BCS stands for Bardeen, Cooper, Schrieffer, the three physicists who did it. So the BCS theory, the B is Bardeen. So John Bardeen won it twice in physics, but Marie Curie is the only one who won the Nobel Prize in both physics and chemistry. So that's an absolutely amazing accomplishment. Again, Marie Curie worked under tremendously bad conditions. Her radioactive fingerprints in some pages can still be seen in notebooks. All right, and so Marie Curie's radioactive fingerprints can still be seen in some of her notebook pages. And she suffered from radiation-induced lesions. So again, Marie Curie suffered from radiation-induced lesions. I mean, again, she was handling radioactive materials with her bare hands. Nobody would do that, right? But unfortunately, and she's not a person to quit. She was an extremely hard worker, extremely hardworking physicist, and would never stop. She worked to the day she died. And so, and she actually died of leukemia in 1934, likely caused by this radiation exposure, right? So again, you can only play with handle radioactive materials so long before it finally takes the ultimate toll on, right? So she got the ultimate toll. She passed away in 1934, and again, based upon leukemia, which is a cancer that likely was caused by her exposure to radiation. All right. So Marie Curie, and I spent a lot of time on Marie Curie because she's massively important. So Marie Curie died from leukemia in 1934, likely caused by her high and consistent exposure to radiation. Right. And so, again, she paid the ultimate price. Interestingly enough, so here her husband Pierre and her. So Pierre won a Nobel Prize in physics with Marie Curie. Marie Curie won a Nobel Prize in physics and chemistry, and her daughter Irene and her son-in-law Frederic Joliot-Curie also won the Nobel Prize in chemistry. So her daughter and son-in-law won a Nobel Prize as well. You had an incredible family legacy of Nobel laureate scientists. So beyond all this, the 1935, the year after the great Marie Curie passed away, Marie Curie's daughter, Irene Curie, Irene, and her son-in-law, Frederic Joliot-Curie, won the Nobel Prize in chemistry. So some serious genetics in that family. For the discovery of artificially induced radiation. All right. So again, a lot of history here, but it's important to appreciate the work done by the great Marie Curie, and again, the Curie family. Uh, Pierre Curie, and Pierre Curie actually did a lot of work in magnetism as well. There's what's called the Curie temperature that deals with superconductivity. That's Pierre Curie. Marie Curie, again, I talked all about her, and even her daughter, Irene Curie, and son-in-law Frederic Joliot-Curie. Were also Nobel laureate scientists. All right. So, okay, so we talk about these. Let's talk about more of the specifics of this radiation. All right. So a lot of what I've talked about has been history, but let's talk about what is actually coming out of the nucleus of the atom. All right. So The so the research really began with Lord Ernest Rutherford again. We've talked about him. A lot of the research of what is the radiation. What is the nuclear radiation? What forms is it in? A lot of that research was done by again Lord Ernest Rutherford. All right, and so again, we want to ask the question: what is this radiation? So research, changing topics now, began by people such as New Zealander Ernest Rutherford. So basically, research into the nature of the nuclear radiation, or of nuclear radiation, began with people like Lord Ernest Rutherford. Okay, so again, Ernest Rutherford is another one of these superstar scientists. Eventually, it was discovered there are three types of radiation, or three types of nuclear. So eventually, it was discovered so three types of radiation were distinguished. And they're named alpha, and with the Greek letter alpha, beta, here's the Greek letter beta, and gamma. And we have the Greek letter gamma. Right? Because like X-rays, their identities were initially unknown, right? That's why we call them X-rays. Well, here's three more unknowns. Because like X-rays, their identities were initially unknown. All right. So with the work done by people like Rutherford, we see that there are three types. The radiation comes in three different forms: alpha, beta, and gamma. All right. Now, Rutherford did a number of tests. One of the first things he did is he passed the rays through a magnetic field. He saw the gammas were unaffected while the alphas and betas were deflected in opposite directions, indicating the alphas are positive, the betas are negative, the gammas are uncharged. Okay, that's his first test he did. So he was able to generate alphas, betas, and gammas. Alpha radiation, beta radiation, gamma radiation. He passed each of these types of radiation, these rays, through a magnetic field. All right. So again, if rays were passed through a magnetic field, again, we don't know what these are yet. Rays were passed through a magnetic field. The gammas were unaffected. while the alphas and betas deflected in different directions. Indicating they had opposite charges. They're oppositely charged. And again, we understand that by the Lorentz force law. QB cross B. Depending upon the charge, you either deflect one way or the other. You know, we talked about that in our studies of electromagnetic theory. So when you pass a particle through a magnetic field, well, the gamma rays being unaffected means that the gamma rays, whatever they are uncharged. The alphas have one charge and the betas have another. Again, QB cross B, right? How you know, again, QB cross B, you know, it's either you're going to have a deflection force one way or the other, right? Again, that's just based upon the magnetic force law. So Rutherford used both magnetic and electric fields to show the alphas have a positive charge twice the magnitude of an electron, or positive 2 Q sub E. All right. So Rutherford did further experiments. So first of all, you know, he did the first test to show, yeah, okay, they had opposite charges. So then Rutherford got more advanced. Rutherford did further experiments to use both magnetic and electric fields. And he showed that the alphas had a positive charge that was twice the magnitude of the electron. So he used magnetic and electric fields and showed that the charge of the alpha particle, or the charge of the alpha particle, was positive and had twice the charge of an electron. Or another way of saying is positive 2 absolute value of Q sub E. All right. So Q sub E is the charge of the electron. Take the absolute value of that, multiply it by positive 2. That is the charge of the alpha particle, whatever it is. And we don't know what it is yet, you know, at this time. So he also found he also found that the alpha had a charge to mass ratio several thousand times smaller than the electrons. Okay, and so he also did, you know, Thomson's experiment. Rutherford found that the alpha particle had a charge to mass ratio. And very important at this time, you know, before the work that was done by Millikan, you know, the alpha particle had a charge to mass ratio. Several thousand times smaller than the electrons. So that shows that the alpha particle is much more massive than the electron. And Rutherford found that the alpha particle had a charge to mass ratio several times smaller than that of the electron. Again, trying to figure out what it is, doing science. Okay, so we understand the charge to mass ratio. He collected some alpha particles from a radioactive source, and he passed electric discharge through them. And he obtained the same spectrum as the recently discovered helium gas. All right, so what did Rutherford do? He used electric field and magnetic field, was able to determine that the charge of this alpha particle had a mass of I'm sorry, back up. He used the magnetic and electric fields to show that the charge of the alpha particle was positive and had twice the charge of twice the magnitude of the charged electron. Positive 2, absolute value of Q sub E. He found that out by doing some electromagnetic tests, and very similar to the kind of tests that J.J. Thomson did. Crossing electromagnetic electric field to magnetic field. We've talked about that in chapter 30. He also found that the alpha particle had a charge to mass ratio several thousand times smaller than that of electrons. So charge to mass. If it's several times smaller, that means the mass is much bigger. The mass of the alpha particle is much greater than that of the electron. And then Rutherford further collected a bunch of alpha particles and ran a gas discharge through it. He collected a gas of these alpha particles. All right, so then Rutherford, this is very beautiful scientific reasoning here. Rutherford then collected a gas of these alpha particles. And gas is just a bunch of particles that are in a vessel that do not interact with each other, like an ideal gas, right? So he collected a gas of the alpha particles into in a gas discharge tube. And discovered that it had the same spectra as the recently discovered helium gas. So altogether, the alpha particle, the emission of alpha particle, is the emission of a helium nucleus. So essentially, altogether, Rutherford discovered the alpha particle is actually a helium nucleus. That's what this tells you. So altogether, Rutherford discoveries point to the alpha particle being a helium nucleus. So alpha decay is a nucleus emitting a helium nucleus. All right, and so it emits a helium nucleus and transforms to another element. Why? Because a helium nucleus has 2 protons and 2 neutrons. So if you change the number of protons, then you become a new element, right? An element depends on how many protons are in an atom. So clearly, if you're giving off a helium nucleus, there's a new element that's formed. So originally it was one element, now it's a new element plus the helium nucleus being emitted. Okay, that's called alpha decay. So for this work, Rutherford won the Nobel Prize in chemistry in 1908. So for his work with alpha particles, or alpha decay, Rutherford won the Nobel Prize in chemistry. In 1908. All right. So, and he continued making great contributions until his death in 1934. Right. So, the great Marie Curie and Rutherford both died in 1934. All right. So Rutherford continued making great contributions in science until his death in 1934. 1934 was kind of a sad year in physics. Both Marie Curie, and Ernest Rutherford passed away that year. That's pretty sad there. So now that's alpha decay. We know what's a helium nucleus due to the work done by Rutherford, for the most part. Then we have beta decay. Now, beta decay, researchers did a lot of work they did some work to prove that beta decay was really negative, had the same mass and charge mass ratio of the recently discovered electron. So beta decay is the emission of a highly energetic electron. All right, and so again, same kind of experiments, if you will, were performed there. So other researchers had already proved that betas are negative. I mean, basically, clearly, if they deflected the opposite way of an alpha particle, and Rutherford's experiment, if he determined alphas were positive, then of course Rutherford himself would understand that betas were negative as well from the previously explained experiment. But proved that betas are negative. Again, we don't know what betas are yet, but they're definitely negative, and they have the same mass and charge to mass ratio as the recently discovered electron. mass and charge to mass ratio. A lot of this research was done right at the turn of the century. All right, so altogether, by 1902, okay, not very far into the 20th century, by 1902, it was recognized that beta radiation was the emission of an electron. All right, so again, we're talking, pretty early. So by 1902, it was recognized. It was generally recognized. That beta radiation was the emission of an electron. From the nucleus. So again, another way that a nucleus tries, a nucleus is doing this because it's in a state of instability. It's trying to stabilize. All right, so there's just different modes available to it. Alpha decay, beta decay. All right. Now, interestingly enough, although beta particles are electrons, they do not exist in a nucleus before it decays. They're not ejected atomic electrons. The electrons are created in a nucleus at the instant of decay. They can't exist in a nucleus because that would violate the Heisenberg uncertainty principle. So they're actually created at the moment of decay. They are created in the nucleus at the moment of decay. They do not exist prior to their decay. All right. So although beta particles are electrons, they are created at the moment of decay. They do not exist in the nucleus prior. So they are created in the nucleus at the moment of decay. One of the cool things about particle physics is that particles just get created during the decay process. They didn't exist before, now they exist. Almost a little bit of magic there to some extent. All right. Now, what about gamma radiation? All right, so we talk about alphas, betas. So alphas again are the emission of a helium nucleus. Rutherford did the experiments to prove that. Betas, very early on, were understood to be the emission from the nucleus of a highly energetic electron. The electron is created at the moment of decay. What about gammas? Well, first of all, as I said earlier, gamma rays are not affected by electric and magnetic fields. So gamma rays, whatever they are not charged. So gamma rays are not charged. In order to participate in electromagnetic theory, an object, an entity must have a charge. Okay? So it does not participate in electromagnetic theory. It is not charged. Okay. Now, evidence grew that so essentially it was thought that gamma rays were highly energetic photons. All right, so in a way, even though they are not charged, they're still, if they're photons, they're electromagnetic waves, so they're still an electromagnetic phenomenon. All right, and so it was thought that gamma rays were photons. And photons are uncharged, right? And evidence grew of this until 1914. Rutherford proved it. All right. So evidence of this concept grew until it was proved by Rutherford. In 1914. Okay. So Rutherford scattered radiation from a crystal and observed interference. All right. So Rutherford scattered gamma rays from a crystal and observed interference. Just like it was light, right? So gamma radiation is the emission of a high energy photon by a nucleus. So altogether, gamma radiation is the emission of a high energy photon by a nucleus. In fact, as we've talked about before, it is the most energetic photons, the most energetic electromagnetic radiation that you could possibly have. That's what it is. Gamma radiation, the emission of high energy photon by the nucleus. Again, work done by Rutherford. Rutherford did this in 1914. So again, Rutherford, I say a lot about Rutherford. I mean, he's one of the most brilliant experimental physicists who ever lived. He actually had 6 of his, so again, Rutherford himself is a Nobel laureate. Rutherford had 6 graduate students who became Nobel laureates. So obviously Rutherford, besides being a brilliant physicist, was a brilliant teacher as well. All right. So now, interestingly enough, there's kind of a little bit of an analogy of the creation of gamma rays in a nucleus to X-rays in an atom. So you look at what's called the shell theory of the nucleus. The nucleus itself has excited states. When a nucleus goes from an excited state to a lower energy state, it emits a gamma ray. In the same way that an atom going from a more excited state to a lower energy state emits an X-ray. So there are quantum energy levels inside of a nucleus. There is a quantum mechanics of quantum mechanics of the nucleus with energy levels and energy states, just like there is for an atom. All right. So interestingly enough, I mean, that's the usual nuclear theory is usually called the shell theory of the nucleus. All right, I'm not going to even begin to talk about shell theory here, but nuclear theory is usually the shell theory of the nucleus. So in that sense, gamma radiation comes from the de-excitation of a nucleus. So gamma radiation comes from the de-excitation of a nucleus. Just as X-rays come from the de-excitation of an atom. So there is, so oftentimes, you know, when you see something that gives off a gamma ray, it's because after the nuclear reaction, the nucleus that's left is, you know, in the terms of the of nuclear theory, you know, the atom or the nucleus that gives off a particle or gamma ray is called the parent, and the resulting nucleus is called the daughter. Oftentimes, in many ways, in many reactions, the daughter is left in an excited nuclear state, excited nuclear energy state. So in order to de-excite, it has to give off an X-ray. So oftentimes you give off X-rays because the daughter is in an excited state. All right, and so I'll talk more about that in a moment. All right, and so to kind of sum everything up, we also talk about, you know, so okay, so we have these particles. We have these three types of particles now. We have the three types of nuclear radiation: the alpha, the beta, and the gamma. Now the question is, okay, so now we know they exist. What effect do they have on people? What effect would they have on you if you are nearby? All right, and so they have different. So the thing about these, all of these particles, they actually have the ability, and this is what makes them scary, is they have the ability to ionize, which means that if you were to come in contact with any of the three of these particles, you would have cells in your body ionized, which means that you would have electrons removed from your cells, including your DNA. So that might mess up your DNA, your cell reproduction process. And of course, when that happens, you get goofy cells that form instead, i.e. cancerous tumors. All right, and so you get cells that are not supposed to be forming because the DNA has been altered. All right, and so that's the scary part about these particles. So essentially, all three particles have the ability to ionize. Okay, so let's kind of talk about how these particles would, and this is why Marie Curie got sick, right? Because she was constantly getting these gamma rays and particles in her system, right? And constantly getting, you know, having her biological tissue being affected, right? So alpha, beta, and gamma radiation all possess the ability to ionize. Materials, including biological tissue. We've talked about this in the past, that Ionization of biological tissue is, again, as I said, not good. It causes cancer in many ways. Affects the reproduction of the cells, alters the DNA. DNA, as we discovered, a few chapters ago, is highly electronic, extremely electrical. DNA is. All right, and in fact, the electrical process, the electrical potentials in electrostatic fields in the DNA molecule are extremely important. It's a highly electrical structure. All right. Now, the alpha. So it's discovered that the alpha particle, the alpha, beta, and gammas all have different ranges or depth or penetration depths. So the question is, what would it take to stop them? You have an alpha particle coming. What might possibly stop it? All right, and so let's take a look at that. So again, they all have the ability to ionize. That means they all have the ability to remove electrons from atoms. So let's look at, it's kind of I'm going to kind of recreate a little table. I'm going to recreate table 31.1 of OpenStack. So type of radiation, and we'll say its range. All right, so alpha particles. Alpha particles, being helium nuclei, given amount of energy, it's going to be a lot harder to, given that they're big compared with electrons, it's going to be harder to have them, go at a very high speed. So they're going to be the particle that has the smallest range. They can actually be stopped by a piece of paper, or a few centimeters of air, or a few millimeters of tissue, biological tissue. So it doesn't take much to stop an alpha particle. So an alpha particle can be stopped by a sheet of paper, a few centimeters of air, or a few millimeters of biological tissue. Again, an alpha particle has an energy of about 5 MeVs. So, you don't want to have a 5 MeV particle coming at you. I mean, that's for sure. I mean, that's enough. Again, a few EVs are enough to ionize an atom. You're having something that's coming at you at 5 MeVs, 5 million electron volts. Again, that's something you don't want to be. You don't want to be in the path of that. All right, beta particles. So, but again, the nice thing about alpha particles is all you got to do is stand off more than a few centimeters away, and the alpha particle is not going to affect you. It's not going to reach you. So just being away by a few centimeters is enough. You're away by a meter. You're away more than enough. From the source that's emitting alphas, they're not going to get to you. That's one good thing about alphas. What about beta particles? Well, a beta particle can be stopped by a thin aluminum plate or tens of centimeters of biological tissue. So very likely an alpha particle is going to go right through you. Or sorry, beta particle is going to go right through you. And as it does so, it's going to be ionizing a whole bunch of atoms along the way in your body. So beta particle is something you do not want inside of your body. All right. So again, it can be stopped by a thin aluminum plate. or tens of centimeters of biological tissue. Gammas are the most dangerous. All right. So gamma rays, you require several centimeters of lead or meters of concrete. They'll go right through you without even a flash of an eyelash. I mean, so again, they require lead, and not just lead like an apron that a dentist will put on you. We're talking about centimeters of lead. All right. So several centimeters of lead. Or several meters of concrete. Are required to stop a gamma ray. In fact, you really never stop it, you just attenuate. All right. So again, alpha particles, you can stop with a sheet of paper, a few centimeters of air, a few millimeters of biological tissue, not too much. Beta particles, much more penetrating, can be stopped by a thin aluminum plate or tens of centimeters of biological tissue. So again, they'll go right through you and wreak havoc in your body. Gamma rays, they're highly destructive. You do not want gamma rays in your body. They can be stopped or at least attenuated. I'm not even going to say stopped. They get attenuated by several centimeters of lead or several meters of concrete. This is a concept of range. The shortest range, of course, is the alpha particle, and then it's the betas, and then the gammas have the longest range of all. And that's the length of penetration. So again, they decay because they're in the MEVs as opposed to just EVs. All right, so the thing is, the range of radiation, again, is defined by the distance that the radiation can travel in a material. All right. So again, I mean, I've said the word, but let me be more direct about it. All right. So the range of radiation. Is defined to be the distance it can travel through a material. All right, so again, that's the concept of range when it comes to nuclear radiation. So range is related to several factors. Of course, the energy, the more energetic a particle is, but also the material that it encounters, and also the type of radiation. All right, and so we'll talk about this. So again, range is related to several factors. And those factors include the energy of the radiation, so the energy, the material that's encountered, Okay. And the type of radiation. There's many factors that go into what the range or the penetration depth is. Okay, so again, range is related to several factors, including the energy of the radiation, the type of or the material, nature of the material that the radiation encounters, and the type of radiation itself. So again, it might be obvious, but regarding energy, talk about each of these. Regarding energy, the higher the energy, the greater the range, if all other factors are kept the same, right? So again, the greater the energy, of the radiation, the greater the range, if all other factors remain the same. Okay. So again, that should seem pretty straightforward to you. I mean, energy, the greater the energy, if nothing else changes, the greater the energy, the greater the range. All right. The more energetic the particle, the more it will penetrate. Now, the amount of the ionization is also proportional to the energy of the particle. All right. So radiation can be absorbed or and another situation here is how much ionization does a particle experience. All right. Again, every single time the radioactive particle ionizes an atom, it loses energy. It attenuates. When it loses energy, performing like a Compton scattering, it loses energy to the electron that it loosens from the atom, which means that's less energy for it. So it then attenuates. So the more ionizations that are performed, the more attenuation that occurs. So materials such as lead are very, very dense, and so there's going to be a lot more electrons that'll be encountered by the radiation, and so a lot more ionization events, a lot more attenuation. So given everything else being equal, if you have a material that has a greater density, i.e. more electrons per unit volume, there's going to be more opportunities for ionization to occur. Every time ionization occurs, the radiation loses energy. So again, that's another factor. All right. So again, more energetic the particle is, the greater the depth of all else remains same. But then again, if energy is the same, the number of ionizations also depend on the depth. So again, ionization affects the energy of the radioactive particle. Or we'll say of the radiation. All right. So understand, it takes energy to ionize an electron. So sorry. It takes energy to ionize an atom. That means remove an electron from an atom. Okay. I.e., remove an electron from an atom. Okay, and so and this energy is at the expense of the radiation. Right? So what's one thing you can do? Well, you can take a material that is like lead that has very high density. So for instance, radiation can be absorbed or shielded by materials. You know, such as lead aprons dentists drape over us. When taking x-rays. I mean, and why does this work? Well, again, it is because the material is very dense, and there's more. So again, materials like lead are very dense. And so there are many more electrons per unit volume. And hence, many more ionization events possible for the radiation. So again, that's just going to suck out more energy from the radiation. So the particle won't get as far because it loses energy faster. All right. So again, this affects the range of radiation. He also we have to talk about the type of particle. All right. So again, I talked about that. So again, the ionization is one. If you have a denser material, you have more opportunities. So again, this is going to reduce the energy more quickly, like something, a material like lead will reduce the energy more quickly because there's many more ionization events, and each of these ionization events takes away energy from the radiation and hence reduces the penetration depth. Okay, and of course the last one is the type of radiation. All right, so again, we talked about the energy of the radiation, the nature of the material, how dense is it, how many electrons are available for ionization events, and then of course the type of radiation itself. All right, so the type of radiation affects the depth. Again, with all other things being equal. All right, so that's the last the last part on this. So the type of radiation, different types of radiation have different ranges when compared with the same energy and in the same material. So you're going to keep the energy and the nature of the material constant, the type of radiation also has an effect. So the different types of radiation have different ranges. Okay. Compared at the same energy and in the same material. So comparatively, and with the same energy and in the same material. Okay. So, for instance, alphas have the shortest range. Betas penetrate further. Gammas have the greatest range, as I said. This really directly relates to the charge and the speed of the particle, right? So again, as I said, alphas have the shortest range. Betas have longer range. Gammas have the greatest range. So what makes these particles different? Well, it has to deal with, with the charge of the particle and the speed of the particle. All right. So again, these particles, or the three types of radiation, have different ranges. Because of their speed, because of their, what their characteristic speed and charge, or their characteristic charge and speed. All right, and that's just the nature of them. So for instance, regarding charge, the more readily a particle can produce ionization, the more quickly it loses energy. So number one, off the bat, you have alpha particles that have a positive 2 q sub e charge. It has a charge right off the bat, so it will interact with electrons because of its charge. And it has twice the charge of a beta particle. So again, the more it can interact and cause ionizations, the faster it loses energy. All right, so right off the bat, we see that the charge of the radiation, of the radioactive part of the particle is a factor. All right, so again, the more readily the particle produces ionization, the more quickly it will lose energy. So, for instance, let's look at the difference in charges. So the alpha has a charge of +2 absolute value of q sub e, or we'll say plus 2 q sub e, we'll say. Two times electron charge. The beta has a charge of negative q sub e. And the gamma has no charge. Okay, so what that means then is that electromagnetic force exerted by the alpha is twice as strong as that exerted by the beta. It's more likely to produce ionization just because of this factor. All right, so just looking at this alone, the electromagnetic force that's exerted by the alpha is twice that exerted by the beta. So that alone is gonna be a factor that's going to directly affect ionization. So basically, the alpha is twice as strong as so the force is twice as strong as that of the beta, and it's more likely to produce ionization, right? So the electromagnetic force from the alpha is twice as likely to produce ionization than that from the beta. All things being equal. Just the charge alone. Okay, so the gamma is chargeless, so it only weakly interacts with it's an electromagnetic wave, it's less likely to produce ionization in any encounter, right? So again, there is no charge of the gamma. So in any encounter, it is less likely to produce ionization, even though it is an electromagnetic wave. All right, so the gamma ray, trying to reason out why the ionization, what causes one particle to have a different depth than another. So per encounter, since the gamma ray is chargeless and an electromagnetic wave, it is less likely to produce an ionization. So the charge comes into play here. All right. Now the So more quantitatively, the change in momentum. So again, putting this all together, more quantitatively, the change in momentum delta P given to a particle. Okay, change in momentum delta P given to by a particle is delta P equals F delta T by Newton's second law. All right. So an F is the force the alpha, beta, and gamma exert for a time delta T. Again, electric force. And F is the force that the alpha, beta, and gamma exert in a time delta T. Again, time delta T, there's going to be a force that's going to be caused by, of course, an electric force, so electrostatic force. All right. The smaller the charge, the smaller F, and the smaller the momentum and energy loss. All right. So again, the smaller the charge, the smaller F, and the smaller the momentum. And energy lost. All right, so again, we're talking about, given that the alpha particle has twice the magnitude of charge as the beta particle, and of course, the gamma ray has zero charge, this affects their ability to ionize. So again, the alpha particle is going to most readily ionize with all things being equal, with everything else being equal on any given encounter with an atom than a beta particle or a gamma ray. Again, the more ionizations, i.e. removing an electron, it takes away energy from the radiation and hence affects the depth of the radiation into the material. All right, so it takes away its energy. Now, so again, the alpha particle is also a big jumbo particle compared with an electron. So again, electron is much smaller, and of course, the gamma ray is going to travel the speed of light. So, in all things being equal, the alpha particle is going to be much more massive, thousands of times more massive than the electron. So, a given amount of energy is going to make the electron or the beta particle go much faster than the alpha particle. Alpha particles typically will go about 5% to 10% the speed of light, whereas beta particles are oftentimes relativistic. And of course, gamma rays, which are photons, go at the speed of light. All right. So all right. So since the speed of alphas speed of alphas is about 5% to 10% the speed of light. We can use classical or non-relativistic formula. So classical, i.e. non-relativistic, formulas apply. And they do not require relativity theory, special relativity. All right. So the speed at which they travel is another major factor for alphas, betas, and gammas. All right. So the speed at which they travel is another major factor for alphas, betas, and gammas. Okay, and really what the reason being is the faster that a particle moves in the vicinity of an atom molecule, the less likely they are to interact. All right, so again, the faster a radiation or a particle moves past an atom or molecule, the less likely it is to interact with it, the less time it spends with it. All right, so the faster they move, the particles move, the less time they spend in the vicinity of an atom or a molecule. And the less likely they are to interact. Okay, so alphas and betas are particles with mass. Helium nuclei for the and electrons respectively. The energy is kinetic, given classically by 1 FmV squared. All right, so the mass of the beta particles is thousands of times less than the alphas, and so the betas must travel much faster than alphas to have the same energy. All right, so betas are faster than they're oftentimes at relativistic speeds. Gamma rays or photons, they travel at the speed of light. All right, and so again, they're for a given energy, they all travel at different speeds because of their mass, right? So again, the speed affects the amount of time that a given particle has in the vicinity of an atom or molecule, and hence less likely to interact with it the faster it is. So again, you have the alpha particle. It's a helium nucleus. It's going to go the slowest. All right, so the alpha particle is a helium nucleus. And it moves the slowest for a given energy. Okay, its kinetic energy is classical. So its kinetic energy can be described by the classical formula 1 f mv². You don't need relativity. And it has a much larger mass. Okay, the beta particle for a given energy is much smaller. It's an electron. All right, so for the same energy, the beta particle is much smaller, much less massive. And it typically moves at relativistic speeds. Okay, the gamma ray is a photon. A highly energetic photon. And of course, because it's a photon, it travels at the speed of light, the fastest possible speed. So the alpha particle will have much more opportunity to interact with atoms and molecules. So it again has, it has much more opportunity to interact and ionize, because it has twice the charge of the beta particle, and because it moves the slowest. It has more time in the vicinity of the atom as it moves along. The beta particle is much faster. It does not spend as much time in the vicinity of the atoms and molecules. And of course, the gamma ray travels fastest of all because it is light. It is electromagnetic radiation. All right. And so again, the amount of time the particle, the radiation spends in the vicinity of atoms and molecules also is a major factor in whether ionization occurs, which of course directly affects the range. All right. So all right, so that's really the nature of the types of radiation. I think I've said enough about these. So now we understand that there must exist a nucleus of the atom for many reasons. I mean, obviously you have the gold foil test done by Rutherford, and there's also the argument that these radioactive particles are coming out of the nucleus at these extremely high energies, too high to be atomic. They have to be nuclear. Okay, so now let's discuss the parts of the nucleus. So what makes up the nucleus? I mean, so again, we've made we understand. I mean, initially it was understood that the nucleus was composed of protons, but there's not enough mass to account for just protons. I mean, if you just say, okay, well, I have an element Z, and well, it's going to have Z protons and Z electrons. Well, if you look at, we understand how much what the mass of a proton is. There's not enough mass to account for the mass of the atom. So there must be another particle. All right, and so the other particle is understood to be a neutron. All right, so again, we're going to discuss the nucleus now, and particularly the substructure of the nucleus is our next topic. So it's amazing enough. I mean, I have discussed that even J.J. Thomson, when he discovered the existence of an electron inside of an atom, was very reticent to publish because it was thought that atoms were indivisible. The very word atom comes from atomos from Greek, meaning indivisible. So here, Thomson is seeing that there is a substructure of the atom. It's composed of electrons. I mean, electrons and protons. Now, he thought there was a plum pudding model. The work done by Rutherford in the scattering of alpha particles off of gold atoms in a gold foil showed that the atom is really a very, very dense positive nucleus with electrons, going around it. Right. That was the model then. But again, if you look at this, we know that almost all the mass of the nucleus, all the mass of the atoms in the nucleus, but there's not enough mass to be accounted for, right? So we understand, again, from the work done by Thomson and Rutherford, the atom is composed of a dense positive nucleus surrounded by low mass negative electrons. Now we know the electrons have very little mass, relatively speaking. So almost the entire mass of the nucleus of the atoms in the nucleus. Again, this is all stuff that we understand from the work done by Rutherford. So again, almost the entire mass of the atom. Is in the nucleus. But, if an atom has an atomic number Z, i.e., Z protons, then there's not enough mass to account. There's not enough mass from the protons to account for the mass of the nucleus. There's missing mass. Well, it turns out there's another particle that is in the nucleus. It has a mass that is very similar to that of the proton, and it has no charge. That mass, or that particle, is called a neutron. All right, and so the nucleus is composed of protons and neutrons. All right, and that was later discovered by the neutron was discovered by Sir James Chadwick. All right, and so the great experimental physicist Sir James Chadwick eventually discovered the neutron. Empirically. Chadwick was one of the physicists that worked on the in the Manhattan Project. So again, he brilliant experimental physicist. And so again, the neutron was understood, and of course, neutron chain reaction is what actually causes the detonation of a fission bomb, of a nuclear bomb. I mean, the neutron chain reaction is what caused the detonation of the nuclear bombs that went off over Hiroshima and Nagasaki. All right. So we have this other particle. So the nucleus is composed of protons with charge positive Q sub E and chargeless neutrons. Another particle the neutron has no charge. The neutron has roughly the same mass as the proton. All right, so if we look at the various masses of these particles, I'll kind of write them up. I'm going to reproduce here Opus X table 31.2. But again, we're talking about the nucleus. Well, if you look at the three major particles that compose an atom, if you will, well, you have so let's see here. We have a particle. I'm going to write this up here. There's a particle. Its symbol. Its mass in kilograms. Its mass in what are called the atomic mass units U, and its mass in MeV over C squared, mega electron volts over C squared. I'll explain all this in a moment. All right, so if you look at a proton, you have a proton, a neutron, and an electron. Again, this is all, coming into this class. Hopefully you've seen all this, but again, this is where we are in our studies of the atom and the nucleus, right? The symbol for the proton is P. The symbol for the neutron is usually N, and the symbol for the electron is E. The mass in kilograms, again, we know these masses very, very well now. The mass in kilograms for the proton is 1.67 262 times 10 to the negative 27. Again, that's in kilograms. Neutron's a little bit heavier, 1.67 493 times 10 to the negative 27, and the electron is tiny, 9.1094 times 10 to the negative 31 kilograms. All right. We have something called the atomic mass unit U. All right. There's atomic mass unit U. You may have seen it in other courses. And I'll talk more about it in a minute. It's given by the letter little u, and 1 U is equal to 1.6605 times 10 to the negative 27 kilograms. Okay, it is chosen such that the mass of carbon-12 is exactly 12U. And again, here we are. I talked about why, sometimes we had a temperature scale. We initially had it based upon some substance that's very, very important. That's called water, the freezing boiling points of water. Well, oftentimes we use a substance that's very important to us. Well, carbon was chosen because of its central importance to the life sciences, its central importance of organic chemistry. So carbon was chosen as a standard because of its importance in organic chemistry. Its importance, carbon is the center of life. So anybody who's taken organic chemistry, what is organic chemistry? That's the chemistry of carbon-based chemistry, basically. Organic chemistry is the chemistry of carbon-based substances. Okay, carbon is at the center. Hydrocarbons, monomers, polymers, so on and so forth. Right. So it's very inconvenient. We notice how small these values are in kilograms. It's almost like it's not so. It's more convenient to actually express these values as U in terms of the atomic mass unit. And so if you do that, you find out that for a proton, you have 1.007276 U. Okay, again, just almost equal to U. A neutron would be 1.008664, just a little bit heavier again than the proton. And the electron is 0.000545858 U, right? So again, I can express the proton, neutron, and electron in terms of kilograms, its mass. I can express it in all three of these particles in terms of U. So I can say the proton has a mass of 1.007276 U. The neutron has a mass of 1.008664 U. An electron has a mass of 0.000548858 U. I express them in terms of atomic mass units. I can also express in terms of use of the Einstein formula, E equals mc squared. So I can express atomic mass units. I can also look at the formula E equals mc squared. And if I look at that, I can say, okay, well, let's take a look here. Using E equals mc squared, all right, I can essentially say, well, in units of mass, I can essentially write the units of mass as, well, I mean, I can write it as, I can write it as basically an E over a C squared. And generally speaking, the units would be MEV over C squared. So for instance, I might say, well, I know that, so essentially, I can say, well, I know that for, let's say, for a rest mass of a proton. Let me give these numbers, and this will make more sense. So for a proton, in terms of MEV over C squared, I have 938.27 for the proton. For the neutron, 939.57. For the electron, 0.511. MeV over c squared. So since it's for a proton, I know what its mass is. This is a mass. Energy over c squared. Those are masses. They don't look like masses, but they are masses. All three of these units are masses. So if I say, I have this mass for a proton. What is its energy? What is its rest energy? Well, it's easy to find. I can just say, well, E equals mc squared. And I say, okay, well, let me plug in and say, oh, am I talking about proton? Okay, that's 938.27. So 938.27 MeV, mega electron volts over c squared times c squared, mc squared, right? C squareds cancel, and I simply just get very quickly 938.27 MeV. So again, it's a very convenient way of getting energies of fundamental particles very quickly. So again, these are just three ways of expressing the rest mass of these particles. Again, these are the rest masses. Okay, think of this as rest mass. This is the mass of the particle in a frame where it is at, in a reference frame where it is at rest. All right. So I also have another useful form. So again, these are the symbols of the proton and the neutron compose a nucleus. The electron goes around the nucleus. These are the three very important particles that are inside of an atom. These are inside of a nucleus. This is going around the nucleus. All right. I have another useful relation. Let me erase this. Another useful relation is I actually have a nice conversion factor, right? I can actually convert a U, one U into an MeV over c squared. So another nice conversion that one can do is we can use a one U, one atomic mass unit. What is it in MeV over c squared? Well, it's 931.5. MeV over c squared. Again, this is just another useful unit. You can derive this very easily. But again, it is something that we can use as a conversion factor in our studies. Okay, now we can actually discuss building a nucleus now. Okay, so a specific combination of protons and neutrons is called a nuclide. Okay, more vocabulary. All right, so a specific combination of protons and neutrons. So the combination of protons and neutrons is called a nuclide. May have heard of this for chem in this class, or maybe you didn't. It's called a nuclide, and it is a unique nucleus. So in this chapter, we're going to talk a lot about nuclides. All right. So again, specific combination of protons and neutrons is called a nuclide. So you can express a nuclide in the following way. And again, maybe, hopefully you've seen this in other courses. We have an element we call X. X, we have so many protons, we call that Z. There are so many neutrons, again, these are subscripts, we call that N. And we have what's called the A is called the mass number, and you typically have seen this. So again, the number of so Z is the atomic number. Well, first of all, let's back up even further. All right, anyway, let's talk about it. So we have, okay, X is an element. From the periodic table. Like calcium. Okay. Z is the atomic number. Again, hopefully you've seen all this nomenclature in other courses. The atomic number, which is the number of protons in the nucleus. N is the number of neutrons. Where? In the nucleus. And A is given by Z plus N. Is the mass number. And it's appropriately named because the entire mass of the nucleus, the entire mass of the atom is really in the nucleus, right? So what's in the atom? What's in the nucleus? Protons and neutrons, right? So it's called is the mass number. All right, so again, this is all stuff hopefully you learn in other courses like chemistry, your chemistry class, if you've had that. But again, these are nomenclatures of nuclear physics, of the nucleus. So X would be an element from the periodic table, like calcium. So the X here would be calcium, hydrogen, nitrogen, fluorine, so on and so forth. Z would be a number given by the number of protons, called the atomic number. N would simply be another integer, because Z is an integer. N is another integer. That would be the number of neutrons, and then the mass number, that's usually the superscript, is Z plus N. And that's the typical nomenclature describing a nuclide. Okay, everything here is about the nucleus. I don't have any information whatsoever about electrons here. Everything has to deal with the nucleus. It is a nuclide. All right. Now, the mass of the nucleus turns out to be nearly equal to the sum of the mass of the protons and neutrons. So again, calling this the mass number makes sense. I mean, it's and then just because. So let me erase this. So calling A the mass number, makes sense in that. So calling A the mass number makes sense. Since almost the entire, or practically the entire mass of the nucleus, or of the atom, is in the nucleus. And the nucleus is entirely composed of protons and neutrons. Okay, so the so in the context, it's particularly convenient to express the masses in units of U. In that case, protons and neutrons have masses pretty close to one U, and so the mass of the atom is really close to AU, right? So it is convenient, particularly convenient, to express the masses of protons and neutrons in terms of the atomic mass unit U. Then the mass of the atom, again, since the masses of protons and neutrons is about, or very close to 1 U, then the mass of an atom with mass number A is then AU. A times U. All right. So again, you can get the mass of the atom pretty easily this way. So for instance, oxygen has a nucleus with 8 protons, 8 neutrons. A would be 16. Its mass is about 16 U. Right. So give an example here. So for example, oxygen has 8 protons and 8 neutrons. So A, which equals Z plus N, is 8 plus 8, or 16. Its mass is close to AU, or 16U. So if I want to find the mass of oxygen, I know U, multiply by 16, I get the mass of oxygen. All right, so it's very convenient. Now, let's look at a few examples of using the new nuclide nomenclature. All right, and so let's look at some examples here. And again, if you haven't, hopefully some of you are familiar with this whole nomenclature, but in case you're not, all right, so let's look at the nuclide nomenclature. Let's look at, for instance, hydrogen. So let's look at hydrogen. All right, now we know what's hydrogen. Well, hydrogen has 1 proton and 0 neutrons. All right, so in this particular context, in the simplest form, one would normally write this. Again, the nomenclature again is the element, number of protons in the subscript, number of neutrons, and the mass number. So for hydrogen, what would you write? Well, okay, so you know that the symbol, you put that in for X. So you have H. Number of protons, put a little subscript 1. Number of neutrons, subscript 0. And of course, 1 plus 0, C plus N is A, 1 plus 0 is 1. Oftentimes, if there's 0 neutrons, like in this case, you just leave it off. All right, so again, a basic hydrogen atom would follow this nuclide nomenclature in this manner. How about helium? Well, what's helium? What's a helium nucleus? Again, 2 protons, 2 neutrons, right? So how do I do this? Okay, well, the chemical element, the chemical symbol, instead of X, I put helium, He. Okay, how many protons does helium have? It has 2 protons. It has 2 neutrons. So again, Z plus N, 2 plus 2, 4. So the mass number is 4. So I would write helium in this way. Helium sub 2 super 4. We can write a special form of hydrogen. We have a heavy hydrogen called deuterium. Sometimes you get what's called heavy hydrogen or deuterium. Again, deuterium is hydrogen that's basically 1 proton and 1 neutron. Okay, called heavy hydrogen. And so what are you going to get? Well, you're going to get 1 proton, 1 neutron. Of course, Z plus N, 1 plus 1 is 2. So again, that is deuterium. So you have, oftentimes you might sometimes call this, sometimes it's called D for deuterium. Some people oftentimes, instead of hydrogen, sometimes they refer to this as deuterium. And sometimes, if you talk about heavy water, this is deuterated water, if you will, or heavy water. And we know the water, of course, right, is H2O. Well, heavy water, or deuterated water as it's called, is sometimes called D2O. Essentially, instead of the symbol for hydrogen, they oftentimes use a capital D for deuterium. Basically, it's a heavy form of hydrogen. There is another form of hydrogen that's actually radioactive. This is called tritium. So we actually have a radioactive form of hydrogen called tritium. How do you get tritium? Well, again, if it's hydrogen, it's got to have 1 proton. But in this case, you have 1 more neutron. We have what's called tritium. It is actually radioactive. It's a radioactive version of hydrogen. It has 1 proton and 2 neutrons. What does it look like? Well, again, it's going to be, the X is going to be, the symbol again will be the chemical symbol hydrogen again for H. Again, if it's hydrogen, it certainly always has 1 proton. Now it has 2 neutrons, and again, C plus N, 1 plus 2 is 3. Okay, so again, tritium looks like that in the new nuclide form. Now, again, we've seen that we have elements that we've seen, as I've shown you here, you can actually have different number of neutrons. And again, this goes back to hopefully terminology you learned in previous and other courses, but there's a special name for elements that have, that have the same number of protons. They have to be because they're same elements, but a different number of neutrons. We refer to those as isotopes. All right, so nuclei. Nuclei such as hydrogen, deuterium, and tritium. the same number of protons. Same number of protons, but different number of neutrons. Such elements are said to be isotopes. So again, a term that hopefully you learn in other courses. So again, same number of protons, different number of neutrons. Now, if you look at this nomenclature, there's actually a built-in redundancy. So again, this nomenclature is heavier than it really needs to be. So for instance, there's a built-in redundancy here, right? And so if I look at this nuclide nomenclature, if I know, so if we know, all right, so let me back up. There's a built-in redundancy. And the nuclide nomenclature. So for instance, if we know if we know the elements, we can determine Z. From the periodic table. So you tell me, oh, the element's sodium. Okay, I look at the periodic table. Ah, that's 11. So I just knowing that the element is sodium, I automatically know that Z equals 11. I can look at that up in the periodic table. So we can determine Z by looking at the periodic table. Likewise, if I know then once we know Z, and say we know A, then we can determine N. And N would be what? It'd be A minus Z. So all I really need is the chemical symbol and the mass number. That's really all I need. If I know the chemical symbol, then I can look up the periodic table and determine Z. If I know the mass number, then all I have to do is subtract Z that I found from the periodic table, and I now can understand the number of neutrons. So again, this is a more heavy of a nomenclature than you really need. In general, oftentimes you see when you talk about nuclear reactions, you usually see nuclei just given by a chemical with a little number on top that tells you the number of protons and neutrons. And this is all you need to know. That is as deterministic as you need to be. So for instance, let's take a look at uranium-238, for instance. Okay, let's say, for instance, I know uranium-238. All right, and let's kind of figure out, can I understand what the number of protons, what the number of neutrons are, if all you give me is, you tell me it's uranium-238. So first of all, when I read something like this, 238 uranium, okay, it's read backwards. It's read as, you see the number coming first and then the symbol. It's read as uranium-238. Okay, so what do? Well, I look at the periodic table. All right, so I look at periodic table can see that uranium is element number 92. Great. So what does that tell me? Well, that means now I know that Z equals 92. Can I just look at the periodic? Oh, you told me it's radium. Oh, 238. Okay, well, that tells me the number of protons plus neutrons. So what do I know now? Well, I can find the number of neutrons because I know the mass number A, and I subtract the atomic number Z from it, and that simply becomes an arithmetic problem. It's 238 minus 92. And from this information, I can determine that the number of neutrons is 146. So I now can dress up and say, well, I could dress this thing up in full regalia, if you will, and say, well, I know that there's 92 protons and 146 neutrons. But again, as you can see, it's more information than I really need. All I really need to do is say the uranium-238 is this. All this other information I can determine. All right. And so again, usually you're not going to see uranium-238 dressed up like this. Usually you're going to see it dressed up like that. All you need is the chemical symbol and the mass number. All right. So again, that is the nomenclature that you see for nuclides. All right. Now, how big is a nucleus? So again, so we understand. So what do we understand about nuclei so far? We understand that they emit radiation. We understand they emit radiation in 3 types: alpha, beta, and gamma. The alpha, beta, and gamma all have different penetration depths, which we call range. We also know that the nucleus is composed of protons and neutrons. Protons and neutrons have roughly about the same masses. I gave you the exact masses, or the very precise measures, I should say, earlier. And we can also dress up. We can also describe a nuclide, which is a unique nucleus. Number of protons, neutrons determine a unique nuclide. We have the nomenclature to basically describe any kind of nucleus in this manner. Now, another question you might ask is, well, how big is a nucleus? I mean, is there a way to mathematically, or at least empirically, through some sort of a formula, determine that? And the answer is yes. There have been a number of experiments that essentially show you that a nucleus, as you can imagine, is about the densest material in the universe. You are basically shoving together these neutrons and protons as closely as they can possibly fit together, with pretty much no space in between. They are close packed. If anything in the universe is close packed. All right. So first of all, let me give you one more terminology before we move on. So we talk about neutrons and protons. They're the constituents of a nucleus. So the constituents of a nucleus and new vocabulary word are called nucleons. Nucleons, all right? Protons and neutrons. Are collectively nucleons. Okay, so again, anything that lives in a nucleus, calls its home in a nucleus, is called a nucleon. All right, so again, vocabulary word for you. Now, number of measurements have been conducted on atoms, on a nucleus of atoms in particular, and from all we can understand, they are a very tightly packed ball of nucleons, very tightly packed. All right, and so a variety of experiments indicate that the nucleus behaves something like a tightly packed ball of nucleus. Okay, the nucleons have large kinetic energies and move rapidly when in very close contact. So not only are these nucleons packed together, they are moving extremely fast. They have very high energy. So the nucleus of an atom is highly dynamic. All right, and so it's another way of looking at these nucleons is they move around very, very fast. So these nucleons have large kinetic energy. So it is a dynamic model. And thus move rapidly in very close contact. That's another thing. Nucleons can be separated by a force such as a collision with another nucleus, but resist strongly being pushed closer together. So you can remove a nucleon, but they very much resist being pushed into one another. All right. So nucleons can be removed. It is possible to remove one. It can be removed from the nucleus via a collision with another nucleus, for instance. But they strongly resist being pushed into one another. Okay. Now essentially the most compelling evidence that nucleons are closely packed in nucleus is the radius of the nucleus. All right. So we actually have a formula that has been empirically determined to give you the radius of the nucleus. All right. And so again, this is great evidence. I'll explain why that is in a moment. So again, they're the model here is they're very tightly, nucleus a very tightly packed ball of nucleons. All right. So tightly packed that they're literally in a ball, and inside of them, they're moving very rapidly. All right. The most compelling evidence that nucleons are closely packed in the nucleus. Okay. Is that the radius of a nucleus radius of a nucleus, R, is found to be approximately given by so R is R naught A to the 1/3. Okay, R naught is 1.2 femtometers, i.e. 1.2 times 10 to the negative 15 meters, and A is the mass number. Same mass number I talked about a moment ago. All right. Now, why is that so compelling? Well, if you think for a moment here, let's imagine that we're talking about a ball. What would the volume of a ball be? All right. So it's kind of imagine here that okay, R is R naught A to the 1/3, the radius of the nucleus, right? So let's kind of imagine here for a moment. I'll kind of write this formula kind of in a parking lot, and let's kind of determine what this means. So again, we have an R equals R naught A to the 1/3, and R naught is given as 1.2 femtometers. Some people would call that 1.2 fermions. Let's imagine here that I have the volume of a sphere, 4/3 pi r cubed, right? Well, imagine a volume of a sphere 4/3 pi r cubed. What does that mean? Well, it means that the volume again, volume of a sphere. Now I'm going to kind of be a little rough here. Say the volume goes as r cubed. Okay, well, what do we know about r? Well, that would mean the volume would go as what? Some constant cubed, a to the 1/3 cubed, right? Cube of a product is a product of the cubes, right? And so a to the 1/3 cubed, that's just a. That means that the volume goes as some constant, whatever it is, times a, or basically the volume goes as a. The volume of the nucleus goes as the mass number. All right. So again, this tells you that literally I am literally, the volume is absolutely directly determined by the mass number, by the number of nucleons, and there's no extra space at all. There's jammed packed as close as you can get, right? So literally the volume of a nucleus goes as the mass number. All right, they essentially you're packing nucleons as closely together, and there's no empty space between it. All right, so again, let me write this up here. The volume of the nucleus goes as a mass number. I mean, effectively, what this means is that the nucleus is being so closely packed with nucleons that there is no space in between. Very crowded place. It is as closely packed as you can imagine. All right. I'm going to do an example from OpenStax. I'm going to do OpenStax example 31.1. Kind of get an idea of the density and size and density of the nucleus. All right. So let's do an example to kind of put this into terms of numbers. All right. OpenStax example 31.1. Okay, I'd like to know, A, find the radius of an iron 56 nucleus. Number one. B, find the approximate density in kilograms per meters cubed. Approximating the mass of iron 56 to be 56U. In iron 56, I put the mass number first and then the symbol for iron. Latin, it stands for ferrum. All right, so again, we're going to talk about iron 56, the iron 56 nucleus. Find the radius of an iron 56 nucleus. Again, we gave the formula a moment ago. And then find the approximate density in kilograms per meters cubed, approximating the mass of iron 56 to be 56U. All right, so remember that. I'm going to erase the board here. All right, so let's find the radius of an iron 56 nucleus. So how do we do that? Well, again, R is R naught, A to the 1/3. Okay, that's going to be 1.2 femtometers times 56. That's number of nuclei, a mass number, to the 1/3 power. Okay, R, when I do that, is equal to 4 point, is well, R is 1.2 times 10 to the negative 15 meters times 56 to the 1/3. I find R to be 4.59 times 10 to the negative 15 meters, or 4.59 femtometers. And just a direct relationship, direct application. And again, that's 56 nucleons. 56, all shoved together. Now let's find the volume now of this iron nucleus. So V, again, we're going to assume it's a sphere, 4/3 pi r cubed. I want to find the density of it, right? So mass divided by volume. So let's get the volume first. 4/3 pi times this number, 4.59 times 10 to the negative 15 meters quantity cube. I get the volume of this iron nucleus is 4.05 times 10 to the negative 43 meters cubed. I mean, that is just a massively small volume. All right, the mass of the iron. Again, we're going to say it's 56U, right? That's 56 times 1.6605 times 10 to the negative 27 kilograms. That becomes 9.299 times 10 to the negative 26 kilograms. All right, we're ready to find the density. The density is just the mass divided by the volume. All right, so that's the 9.299 times 10 to the negative 26 kilograms divided by 4.05 times 10 to the negative 43 kilograms. And I find the density to be 2.3 times 10 to the 17th kilograms per meters cubed. Again, how did I do this? Found the radius of the nucleus by this formula, R naught, a to the 1/3. Now we want to find the density. I find the volume, assuming that it's a sphere, 4/3 pi r cubed. The mass, I'm assuming, is 56U, because I know that the iron atom has, iron 56 is 56 nucleons. I'm assuming each one of them is worth, each nucleon, it has a mass of U, atomic mass unit. Rho is the mass over volume. You get this huge density, 2.3 times 10 to the 17th kilograms per meters cubed. All right, let's just kind of talk about this density for a moment. You know, again, this is just a number, but let's kind of size this number up. I mean, 2.3 times 10 to the 17th. Let me just kind of write this one more time. Okay, so again, we found the density. We found the mass density of an iron nucleus, of an iron 56 nucleus. To be rho is 2.3 times 10 to the 17th kilograms per meter cubed. All right, this value is 2 times 10 to the 14 times greater than that of water. All right, to give you an idea, 1 cubic meter of nuclear matter, 1 cubic meter of nuclear matter like this, at this incredible density, okay, has the same mass as a cube of water, 61 kilometers on a side. So 61 kilometers, I mean, it's roughly, I don't know, like certainly greater than the distance across Dallas-Fort Worth. Imagine a cube of water whose side is that big, whose side is 61 kilometers, 61 kilometers by 61 kilometers by 61 kilometers. The mass of that cube of water would be equal to the mass of 1 cubic meter, 1 little cubic meter of this nuclear matter. So there is no kind of densities that we can even imagine at the macroscopic level that is like the densities of nuclear matter. That is one of the things that makes nuclear matter just absolutely so amazing, is that there's nothing that we can compare it with. All right. So, okay, so then the next topic I like to talk about here then is, so we have, if you think about this for a moment here now, so we have a bunch of nucleons shoved together in an extremely small space. All right, and what this really gets down to is that there's a lot of protons shoved together in a very small space. Protons don't like to be near each other. So if you're talking about that there is all of these protons that are repulsive to one another, they all have positive charges, they all repel each other, yet somehow all of these protons can exist in this extremely small space. So that tells you that there must be some nuclear force that's even greater that's holding them together, a nuclear force that we did not yet know about. Again, walking into physics one, the only fundamental force we knew was the force of gravity. Then, as we know, we progressed through a majority of this class. We talked about electromagnetic force, but now we find out that there are actually two more forces inside the nucleus to hold it together like this. So the question really comes down to is, what forces hold the nucleus together? Right? So the nucleus is very small, and its protons being positive exert tremendous repulsive forces on each other. Okay, as I just said. So again, the nucleus is very small. And the protons in this small nucleus exert tremendous electrostatic repulsive forces on each other. All right. So again, the idea is you're shoving together a lot of nuclei together. So again, recall force of electric goes as 1 over r squared. Okay. Since r is so small in a nucleus, F sub E is tremendous. I'm here dividing by numbers like 10 to the negative 15 squared. So again, that is a very, very small a very small denominator. So eventually, what you have to think about is, as we have studied this problem even further, we actually find out that there's not just one nuclear force that was undiscovered, but two. And how do we know this? Because there are two different major modes of decay. There's one, the alpha decay, which is directly related to one of these nuclear forces, and there's beta decay, which is directly related to another one of the nuclear forces. All right, and so judging from the nuclear radiation, we actually know that there are actually two types of nuclear forces. There are two more fundamental forces. As we said, there are four fundamental forces The ones we've known about so far are gravitation and electromagnetic force. Those are long-range forces. Now you have these forces that are very short-range. So the answer, so there are two previously unknown forces that hold the nucleus together. Okay, and make it into a tightly packed ball of nucleon. All right. These forces are called the weak and strong nuclear forces. All right. The nuclear forces are so short range that they fall off to zero strength. The nucleons are separate about only a few femtometers. So they're very, very short range forces. All right. So they're only in a nuclear range. So nuclear forces are so short ranged that they fall off to zero at distances greater than a few femtometers. All right. So now of course, they are like glue. So they're actually, the strong nuclear force is about 100 times more attractive than the repulsive electromagnetic force. So strong nuclear force more than easily holds together the nucleons. All right. So the attractive strong nuclear force, again, it acts on nucleons. It acts on particles because they are nucleons. Because remember, the fundamental forces, they act because the particle possesses a certain property. Well, because these are nucleons, nuclear forces act on them. It has nothing to do with electromagnetic force. It is a nuclear force. It acts on nucleons, protons and neutrons. Charge does not matter. It has to be a nucleon, right? So the attractive strong nuclear force acts on nucleons. And it is about 100 times stronger than the repulsive repulsive electrostatic force between the protons. All right. Thus, strong force easily holds nucleons together in a nucleus. It easily exceeds the repulsive force of the very closely packed proton. Now, also, nuclear forces get extremely repulsive if nucleons get too close together, making nucleons strongly resist being pushed inside one another, something like ball bearings. Right. So another thing too is that nuclear forces become extremely repulsive. Um, if they get too close. Right. Making nucleons strongly resist being pushed inside one another. Like ball bearings. All right. So again, nuclear forces are extremely attractive. The force that acts on the strong force that acts on nucleons. It's about 100 times more, 100 times stronger than the repulsive electrostatic force between the protons in the nucleus. Thus, strong force easily holds nucleons together in the nucleus. Nuclear forces become extremely repulsive if they get too close, making the nucleons strongly resist being pushed inside one another, like ball bearings. All right. So again, that's how these nuclear forces work. Now, also, the very fact that these nuclear forces are so strong accounts for the very large energies emitted in nuclear decay. All right. And so again, that's one of the ways we can answer why the nuclear decay has such high energies. Because the fact that nuclear forces are very strong. I mean, that accounts, it's responsible for the very large energies emitted in nuclear decay. So for instance, let's say during decay, forces do work. So why is this? So during decay, we can understand this from the physics that we already had previously studied. The forces do work. Nuclear forces do work. Okay? And since work is force times the distance, again, recall that work is F dot D, or FD cosine theta. Remind us of that definition of work. A large force can result in a large emitted energy. Large force, large energy. So a large force can result in a large emitted energy. All right. So, in fact, we know again there are actually two forces because there's two modes of decay. So that's why we know there are two forces, the strong and the weak. So, in fact, we know there are two distinct nuclear forces. Because of the two different types of nuclear decay. Okay, and the strong nuclear force is responsible for the alpha decay. And I'll talk more about this toward the end of the chapter. We'll talk about what's called quantum tunneling. I'll explain how alpha decay works. But the strong nuclear force is responsible for alpha decay. While the weak nuclear force is responsible for beta decay. Again, I'll give more details about this as we move along in this chapter. Okay, so again, in fact, we know there are two distinct nuclear forces because of the two different types of nuclear decay. The strong nuclear force is responsible for alpha decay, and again, I'll give more details about that toward the very end of this chapter. And the weak nuclear force is responsible for beta decay. All right, so now, in principle, a nucleus can have any combination of protons and neutrons. There's a definite pattern for those that are stable. All right, and so So again, we see that some of these nuclei end up emitting radiation, and others are not radioactive. And so, why is that? So, so in principle, all right, a nucleus can have any combination of protons and neutrons. But there's a definite pattern for those that are stable. All right, and for low mass nuclei, there's a strong tendency for the number of neutrons and number of protons to be nearly equal. It means the nuclear force is more attractive when n equals z. All right, so if you look at low mass nuclei like helium, lithium, the very beginning of the periodic table. For low mass nuclei, there's a strong tendency for n and z to be nearly equal. It means that a nuclear force is more attractive when n equals z for this case. All right, so again, for low mass nuclei that are toward the bottom or the beginning of the periodic table, we find a tendency that the number of protons and number of neutrons are balanced. All right. Now, we actually, if you do a further nuclear analysis, you find out that you even get greater stability when n and z are even numbers. Nuclear forces are more attractive when the neutrons and protons are in pairs. All right, and that's something that is something that is so again, you want to have again, we're talking about low mass nuclei. You want to have for low mass nuclei, you want to have n equals z. You find out there's even a greater nuclear attraction when n and z are even numbers. All right, so more detailed examination, and this goes into physics way beyond the level of this class, but more detailed examination reveals greater stability. When for n and z, I'm sorry, when n and z are even numbers. Nuclear forces are more attractive when the neutrons and protons are in pairs. Attractive when neutrons and protons are in pairs. All right. Now, if the masses get larger, what ends up happening is we find that there's progressively more neutrons than protons in the stable nuclei. Again, everything I've talked about so far is dealing with low mass. So again, for low mass nuclei, we want Z and N to be balanced. And it's, again, the nuclear force is most attractive when N equals Z. It's even more attractive. Nuclear force is even more attractive when N and Z are even numbers. N's an even number and Z's an even number. Basically, it means that their nuclear forces are more attractive when the neutrons and the protons are in pairs. Now we go and talk about higher mass nuclei. We find out that there end up being a lot more neutrons and protons. All right, so for increasingly larger masses, nuclear masses, okay, there are progressively more there are progressively more neutrons than protons. We just showed an example of uranium-238, right? 92 protons, 146 neutrons, right? Now it's one of 92. It's element number 92. That's the largest naturally occurring element. So you see, there's a lot more neutrons than protons. So there are progressively more neutrons than protons. In the nucleus. Now, why might that be? Well, let's imagine for a moment. Now you're talking about, let's talk about something like uranium. Now we're talking about shoving together what? 92 protons that do not want to be near each other. One of the purposes the neutrons serve is to actually create more nucleons to help give you a larger nuclear force to keep the nucleus together, and it also serves to put little more buffer between protons, to make the protons a little farther apart so that they are weaker. The electrostatic force is weaker because the center to center distance between the protons is larger. So again, this becomes a better stability. So again, what happens, or why is this? Well, again, the larger number of neutrons increases the total number of nucleons creating a larger, attractive, strong nuclear force to combat the high electrostatic repulsion of the large number of large number of protons being shoved together in a small space. Compact space. Also, the extra neutrons serve as buffers between the protons making them further apart and less repulsive. So again, for high mass nuclei, higher mass nuclei, we see that there are more neutrons than protons. The more neutrons allow you to have a larger number of nucleons, which give you even a larger attractive strong nuclear force. And the extra neutrons, again, there's a lot of protons being put together into this very small space. And then the extra neutrons serve as buffers between the protons, so that pushes the protons a little further apart, so they don't quite have as large of electrostatic repulsion to each other. So it serves a couple of different purposes. The fact that when there are a lot of protons, and you're talking about a higher mass nucleus, you tend to see there to be a larger number of neutrons than protons. All right. Again, the purpose is you get more nucleons, hence a larger attractive strong nuclear force, and the extra neutrons form extra buffers between the repulsive the electrons, which are repelled to each other, and hence that larger distance between the protons hence reduces the repulsive force. So there's a couple of different purposes served by having there be more population of neutrons than protons for higher mass nuclei. All right, now we also have the case of we also have what are called very stable nuclei, when there's certain numbers of protons and neutrons. Now, this is in the theory. There are certain special numbers of protons and neutrons that are called magic numbers. When the protons and neutrons achieve what's called a magic number, they have a particular special stability. All right. Again, this is predicted in this theory and also in agrees in experiment. So again, this goes beyond. This is nuclear theory. So you can even go further and say, well, there are more steps. So there are especially stable nuclei that possess certain special values of protons and neutrons. Called magic numbers. I'm not even kidding. And you can even say when a number of protons and a number of neutrons both are magic numbers, the nucleus is said to be doubly magic. Kind of reminds me of Disney World, right? Doubly magic. So So I'm not even kidding with it. So if the protons, if the number of protons and the number of neutrons are both magic numbers, the nucleus is said to be doubly magic. So, the only time I ever hear magic being talked about is either with nuclear physics or Disney World. All right. So, all right. So magic numbers indicate a shell structure for the nucleus in which closed shells are more stable. So there's kind of an analogy to the concept of the noble gases, if you will. There are shells in the shell theory of shell nuclear theory. There are shells that become closed shells. Closed shells are said to be magic. All right. So nuclear shell theory has been successful in explaining nuclear energy levels, nuclear decay, and the greater stability of nuclei with closed shells. All right. So again, all of this is referred to as nuclear shell theory. All right. So altogether, nuclear shell theory very successful theory, has been very successful. In in explaining nuclear energy levels. Again, there's a lot of analogies with the nucleus and the atom, right? So it's very successful in explaining nuclear energy levels, just like there's atomic energy levels. We have nuclear energy levels. And we're not going to get into any of this, but I just want to explain to you that, there are a lot of, again, this is a nucleus. The study of the nucleus is truly another application of quantum mechanics, right? So we have energy levels, nuclear energy levels. We have nuclear decay. We can explain nuclear decay again with nuclear shell theory very successfully. And we have and the greater stability of nuclei with closed shells. And talking about magic numbers. So just understand from all of this that there is a very successful, very accurate nuclear theory. It's called nuclear shell theory. And nuclear physics is like atomic physics, it is a quantum theory. All right. So we've been producing ever heavier transuranic elements since the early 1940s. And we have actually produced a very special element with Z equals 118. Z equals 118 is a very specially doubly magic element that has significant nuclear stability. All right. And so again, Z equals 118 was a great goal for a long time. When I was in high school, people were wondering if we actually can achieve a synthetic nucleus of Z equals 118. I mean, again, any nucleus that you create that's greater than 92, there's 92 naturally occurring elements. Element number 92 is uranium. Any other element that's beyond element number 92 is synthetic, and it usually doesn't last very long. One of the goals in physics is like, can we reach that Z equals 118? If we can reach Z equals 118, that is a special island of stability where it is doubly magic. And so that has been achieved. Okay, so again, this was a goal. I mean, this was something that when I was in high school was a dream, and it has been achieved. So we have been producing ever heavier transuranic elements. Since the early 1940s. And we have now produced the element with Z equals 118. Which is, I believe, doubly magic and considered an island of stability. Okay. So I'm going to end this video with working on a few problems here. So let's look at OpenStax 31.8. says, find the radius of a plutonium-238 nucleus. Plutonium-238 is a manufactured nuclide. That is used as a power source on some space probes. Okay, so again, this is a direct application of the formula R equals R naught A to the 1/3. All right. So again, I know the atomic mass. Or sorry about that. Mass number. I know the mass number. The mass number is given to me as 238. Okay, and R naught is a constant. That's 1.2 Fermis or femtometers. And 1.2 instead of -15 meters. I put this in, R is nothing but 1.2 femtometers times 238 to the 1/3 power. I find that to be, when I work this out, R is going to be 7.4 femtometers. That's the radius of this plutonium atom. Okay, let's do OpenStax 31.10. Okay, the unified atomic mass unit is defined to be one U is 1.6605 times 10 to the negative 27 kilograms. Verify that the amount of mass converted to energy, or that this amount of mass converted to energy yields 931.5 MeV. So again, I wrote that number down. Now we're gonna verify it. Note that you must use 4-digit or better values for C and the absolute value Q sub E. Note that you must use 4-digit or better values. Of for C, the speed of light, and the absolute value of the fundamental electric charge Q sub E. All right, so again, the unified atomic mass unit is defined to be 1 U equals 1.6605 to 10 negative 27 kilograms. Verify that the amount of mass converted to energy yields 931.5 MeV, mega electron volts. Note that you must use 4-digit or better values for C and the absolute value of the electric charge, fundamental electric charge. All right. So again, that's the atomic mass unit. We're just verifying that gives you the E equals mc squared that we would I mean that we basically have been that I wrote down and gave you without verifying. All right. So we're going to verify it. So it's basically a check or a proof. So I'm going to use Einstein's formula, E equals mc squared. Okay. And so we're going to use really it's going to end up being E equals UC squared. And so U is 1.6605 times 10 to the negative 27 kilograms. That is the definition, or that is our value for the atomic mass unit. And the speed of light squared, we're going to use the best speed of light we possibly can, 299.792.458 meters per second squared. When I do that, again, I've taken the speed of light as far as I can. So here I have 1, 2, 3, 4, 5 digits of precision. So I can actually write quite a few digits and be legal about it. So I can write this is my calculator. I can literally say 1.4924. And all these numbers are fine. I'm not going overboard on numbers. 1.4924 times 10 to the negative 10 joules. Now let's convert that to MeV. So E is 1.4924 times 10 to the negative 10 joules. Again, we have to now convert and use the electric charge that is a few more digits than I usually do. So we'll use 1 electron volt has 1.6, usually I say 1.60. I need to go a little further, 1.6022 times 10 to the negative 19 joules. That gives me electron volts. And of course, an MeV is just a million EV, 10 to the 6 EV. That's just a metric conversion. So when I work all that stuff out, I find out that the energy is 931.5 MeV as advertised. So when I say the mass, you can say the mass is 931.5 MeV over c squared, hypothetically. That's the energy. If I were to convert all of the mass in one atomic mass unit to energy, that's what the energy would be. That's the energy equivalent of the atomic mass unit. Okay, let's look at OpenStax 31.11. All right, 31.11. It says, what is the ratio? What is the ratio of the velocity of a beta particle to that of an alpha particle? If they have the same non-relativistic kinetic energy. All right. Now, I told you earlier that alpha particles, being as relatively massive as they are not going to have relativistic kinetic energies or relativistic speeds, but beta particles can. We're going to make the assumption here that the energy as such is non-relativistic, such that I can use classical formulas for both the kinetic energy of the alpha particle and the beta particle. So how do I work this out? Well, I'm going to say that the kinetic energy, we're going to say that they have the same kinetic energy, okay? And that's going to be 1/2 m sub alpha b sub alpha squared plus, and that's also equal to 1/2 m sub beta b sub beta squared. And we're going to say the alpha particle and the beta particle have the same kinetic energies. Well, I can automatically cancel out these 1/2s. And what I can do is I can basically rewrite, do a little algebra, and I can write that v sub beta over v sub alpha is the square root of m sub alpha over m sub beta. A couple steps of algebra 1, I just rearranged with the square root. And let's see, what is that going to equal? Well, it's really 4u is the mass of the alpha particle divided by the mass of an electron. That's the mass of the beta particle. All right, and so that's going to be 4. The atomic mass unit is 1.6605 times 10 to the negative 27 kilograms. The mass of an electron is 9.11 times 10 negative 31 kilograms. And I take the square root of that. So again, it's a ratio, so it should be unitless. So kilograms over kilograms is unitless. I find out that when I do that, v sub beta over v sub alpha is going to equal 85.4. That means with the same energy, with the same kinetic energy, the beta particle has 85.4 times the velocity or times the speed of the alpha particle. Why is that? Because it has a much smaller mass. So given that the kinetic energies are equal, the smaller mass of the beta particle is going to be compensated by the larger velocity. I'm going to work two more problems. Open stacks 31.12. All right, so what does that say? That's if a 1.50 centimeter thick piece of lead can absorb 90.0% of gamma rays. From a radioactive source. How many centimeters of lead are needed to absorb all but 0.100% of the gamma rays? How many centimeters of lead? Sorry, spelled out centimeters. How many centimeters of lead are needed to absorb all but 0.100% of the gamma rays? So gamma rays, they're so powerful that all you can really do is just, as far as, having a total stoppage of them, all you really can do is just figure out how you can attenuate them to a reasonable level. All right. So we know that 1.5 centimeter thick piece of lead will absorb 90% of the gamma rays. What does that mean? That means that 10% gets through. Another similar piece of lead will absorb 90% of what got through the first piece of lead. Another piece of lead will absorb 90% of what got through the first two pieces of lead, and so on and so forth, right? The question is, we want to figure out how many pieces of lead we need to get, or how much thickness of lead we need to get, so that all of the gamma rays are absorbed except for 0.100%. So maybe 1.00% is an acceptable threshold. All right. So how do we do this? Remember that one piece of lead is 1.50 centimeters. All right. So remind me, I need a erase for real estate purposes here. Okay. So how do you do this? So essentially, we desire to absorb essentially 99.900% of the gamma rays. Or 0.99900 of the gamma rays. 0.99900 of the gamma rays. That's what we want to do. Okay, that's our desire. 1.50 centimeter thick piece of lead absorbs 90.0% of the gamma rays incident upon it. Okay, so the question then comes like, okay, what does that mean? That means that one piece of lead is going to basically let through what? 0.10. So the question is, well, I want to figure out how many. So again, it's a multiplicative. You know, if I want 2 pieces of lead, what's going to go through? 0.10 squared. I want 3 pieces of lead, what's going to get through? 0.10 cubed, and so on and so forth, right? Every time I put a piece of lead in the way of the gamma rays, it's going to let through 0.10, a fraction of 0.10 of what got through the previous piece of lead. That means if I take n pieces of lead, 0.10 to the n, I want to only let through 0.001. Remember, I want to absorb 99.9% or 0.999. That means that I want to let through 0.001. Every time I have a piece of lead, I let through 10%. You know, basically, for one piece of lead, I let through 10%. And then the second piece of lead, I let through 10% of what got through the first piece of lead. The third piece of lead, I let through 10% of what got through this first and second piece of lead, and so on and so forth. So it becomes a power. It becomes a power law like this. Now, what I really want to do is figure out n. If I figure out n, at least I know how many pieces of lead. I can multiply that number by 1.50 centimeters and figure how thick the lead has to be. Okay, so at this point, it's got to do algebra. So how do I get to n? Well, I'm going to do a logarithm of both sides. So I'm going to take the log base 10 because I see powers of 10 here. So log base 10 of 0.10 to the n is the log base 10 of 0.00100. Now, there's a rule and logarithms. Again, as I've talked about logarithms, well, there's only 3 things that I can do in logarithms, right? One of them is if you see a power on the argument of logarithm, you can actually take that power and turn it into a coefficient. So I can write this now as n log base 10 of 0.10 is equal to the log base 10 of 0.00100. All right. And now all that's left to do is just a little algebra. I'm going to divide both sides by the log base 10 of 0.10. So my n becomes the log base 10 of 0.00100 divided by the log base 10 of 0.10. Okay, when I work this out, I get a very nice number. I get n equals 3. So n equals 3. All right, and so that means that 3 pieces of lead will basically block or attenuate the gamma rays so that only 0.00 or 0.1% of them get through. Okay, so what thickness does this correspond to? Again, this is 3 pieces of lead. All right, 3 pieces of lead. So let me erase this. 3 pieces of lead. Okay, work that out. So now the rest of the problem becomes very easy because now I know a piece of lead is 1.50 centimeters. So what becomes the thickness now? Well, the thickness, I mean, again, it's one more line, but I ran out of room. is just 3 pieces of lead. And how thick is a piece of lead? 1.50 centimeters, right? So the thickness will be 4.50 centimeters. That's how thick the lead has to be for me to be able to attenuate the gamma rays to the incident gamma rays so that only 0.1% get through. Okay, work out one more problem for this video. Opus X 31.16. All right, Opus X 31.16. A. What is the kinetic energy in MeV? Of a beta ray? Traveling at 0.998 C. Almost at the speed of light. Okay. This gives some idea of how energetic a beta ray must be. To travel at nearly the same speed as a gamma ray. Remember, a beta particle has mass. A gamma ray does not have rest mass. B. What is the velocity of a gamma ray relative to the beta ray? Okay, here we go. So, A, what is the kinetic energy in MeV of a beta ray traveling at 0.998 C? So clearly I need to use relativity. B, I'm sorry, this gives some idea of how energetic a beta ray must be to travel at nearly the same speed as the gamma ray. And beta ray has a mass, gamma ray does not, right? That makes a big difference. B, what is the velocity of the gamma ray relative to the beta ray? All right, so again, we have to go back to our to chapter 28 of Einstein's special theory of relativity. All right, so I'm going to erase this for, so remember the 0.998, very close to the speed of light. All right. So the relativistic kinetic energy is given by, remember, gamma minus 1, mc squared. Okay, so we're talking about a beta particle. So the beta particle is the mass of an electron, right? 9.11 times 10 to the negative 31 kilograms. That's the beta particle, which is an electron. All right. So, and gamma, we have to figure out gamma. So, well, we'll just do it all at once. Oh, by the way, let's use the rest mass of an electron. In this particular case, I'm going to use the rest mass of electron to equal 0.511 MeV over C squared. Let's just do that. Make the calculation. All right. So again, I know the electron is this value, but we can also use the electron as set up as an MeV over C squared. Again, you saw that table I put up earlier. So in a situation like this is very helpful, very useful, because I can just go straight to a kinetic energy MeV by using this form of the mass. This is the rest mass of an electron. This is the rest mass of an electron in kilograms. This is the rest mass of an electron in MeV over C squared. They're equivalent. There's just a different nomenclature, a different format of writing. All right. So kinetic energy. Gamma. What is gamma? Well, that's 1 over the square root of 1 minus v squared c squared. What is that? Well, that's 1 over 0.998 squared. And the Lorentz factor minus 1 mc squared. What's m? 0.511 MeV over c squared. That's m. And then multiply by c squared. Well, look how easy that is. You can just literally cancel out these c squareds when you write it in this format. To work this all out, you find out that the kinetic energy of this beta particle is 7.57 MeV. 7.57 mega electron volts, million electron volts. So that's a very, very energetic beta particle. Very energetic to be able to get it near the speed of the gamma ray. Okay. So there is the kinetic energy. It's very, very much relativistic. Now part B. Let's do part B now. Part B says, remember, part B wants to know what is the velocity of the gamma ray relative to the beta ray. Okay, the velocity of the gamma relative to the beta. What is the velocity of the gamma ray? Well, it's electromagnetic radiation. It's a photon. It only travels at the speed of light. And what did we say the velocity of the beta particle is? Well, it's given in the problem as 0.998 c. All right. So these c's cancel out, and I find out that the velocity of the beta over the velocity of the gamma divided by the velocity of the beta, it is going to be 1.002. So they're very close. All right, so that is all I have for this first video.